Yeah, then welcome to lecture number 4 in winter term 24-25 on the Lattice Boltzmann method. And today we are actually coming to something that we can really call Lattice Boltzmann methods. So we are converging on the numerics, but we'll stay in 1D for today. We continue. You need something to write.
Yes.
Okay, but I need it yes. Back. I have it here to sign the papers in a minute. Okay, we continue where we pick up where we left last time with the Navier-Stokes equation. Navier-Stokes. Or the Navier-Stokes limit. The Navier-Stokes limit of the BGK equation. This is where we stopped. And we'll always just write NSE. So this means Navier-Stokes equation. And the Navier-Stokes equation that comes out of the BGK equation has this rho, and because we had with rho the particle density, the actual Navier-Stokes equation has the density, the mass density. So this is kilograms per cubic meter. In order to distinguish it, I put a star here. Yeah. So then we have in here the time derivative of u plus u scalar product on nabla u, and this is the advection of the Navier-Stokes equation. Then we have the potential part, which is the gradient of the pressure. So we have Cs square rho plus, here we have tau Cs, so Cs is the speed of sound, times rho, already taken out, into Laplace u. And in order to see that this is the Navier-Stokes equation, we have just to notice that this here is the pressure. And this here is the viscosity. Viscosity. Yeah, and Cs, the speed of sound, physically, the speed of sound, or the speed of sound square, energy, Boltzmann constant times temperature, and this divided by the mass of a particle. This is the speed of sound. So what we also discussed last time is that tau, the mean free time between collisions, is proportional to the Knudsen number. This is the thing that the fluid dynamics people don't use that much, and the Mach number. Yeah, by the way, Mach was this guy, I think I said this in the first lecture, Mach was this guy who very, very strongly disbelieved in kinetic theory. Yeah, but unfortunately for him, we are still using him. So, obviously, Cs square is, wait, what did I say? Cs square okay, Cs square is, no, wait. I mixed here something up. Yeah, Cs square, okay. I should always be well prepared. I'm just found that I'm not well prepared. Cs square is proportional to 1 over Mach. Why is this the case? Okay, sorry. This thing here, tau times cs square, this is the Knudsen number divided by the Mach number, and this is something that we call the Reynolds number. You just kicked me that I did not think about why cs square is proportional to 1 over Mach. This has to, I have to look this up. Is the Mach number is the velocity? Yeah, the Mach number is the velocity. Of course, I mean the Mach number. The Mach number is of course the velocity. I mean the velocity scale by the speed of sound. Yeah. So and then. Okay, anyway, this entire thing here, if this viscosity, I mean, we can put it the other way around, because viscosity basically is expressed as 1 over the Reynolds number. Yeah? So this is, and the Reynolds number, so the Reynolds number is something that you're probably more familiar with. Okay, by the way, I keep this on the YouTube, that I did not know how to derive this so that my enemies can forever make fun of me because of this. Yeah, I have the because I have the observation. The more I mess up the lectures, the more views they get, and I think this is something. This is something, and that we should use as encouragement for people to actually watch my lectures. I should mess things more up. Okay, homework for you: find out why cs square is proportional to 1 over Mach, and tell me next time. Or if not, then tell me that not. Yeah. So the Reynolds number is something that most of you should know. This is U times L divided by nu. Yeah. So what is nu? U times L. So velocity scale times length scale times density divided by mu, and mu is probably the thing that more people here know as the viscosity. It's the dynamic viscosity. So the dynamic viscosity, mu, is the density, mass density rho times nu, and this is tau cs square rho star. So let's write down u is velocity scale. Velocity scale, L is the length scale. And nu is the kinematic viscosity. Please don't say kinetic viscosity. That's not the kinetic viscosity, it's the kinematic viscosity. So this is by the way, this guy is a proper diffusion constant. Or coefficient. Diffusion coefficient always has units meter squared by second. This is a proper diffusion. Yeah. So we derived at the Navier-Stokes equation in lecture 3. So last week. Under certain under certain assumptions, namely that the Knudsen number is larger than 0, but the Knudsen square goes to 0. This is the assumption that we made to actually derive at the Navier-Stokes equation, which of course means that all of this is true if the Knudsen number is small, but it is finite. Yeah, it's not 0. And this is complicated. Yeah, of course, what does this actually mean? Yeah, small but not 0. Yeah, and is part of the reason why everything related to the Navier-Stokes equation is kind of difficult. You know, if you prove that it has a solution, or you prove that it does not have a solution, you can get $1 million and be, I mean, forget about the $1 million, you will be very, very famous. Yeah, it's one of the, so it's basically considered, I mean, it's a mathematical and a physical problem, and it's one of the most fundamental problems. Richard Feynman said that with turbulence, which basically is coming from the Navier-Stokes equation, yeah, solving the Navier-Stokes equation, is the most fundamental unsolved problem of classical physics. Yeah, and it's still unsolved. So, by the way, one thing we consider all of this at a fixed Reynolds number. So every time we look at a problem, we have a fixed Reynolds number. So Reynolds number Mach by Knudsen. So this is for us, for our purpose, this is a constant. I say this because some of you may have a look in some of these books where they do Chapman-Engskog expansion. We are not doing Chapman-Engskog expansion in this lecture series, yeah, but in the Chapman-Engskog expansion, they consider Reynolds number not to be constant. But you remember when we want to solve a specific engineering problem, yeah, then this has a fixed Reynolds number. It may not have a fixed resolution, yeah, for how we discretize it, but we'll have a fixed Reynolds number, of course. So then, if this is a case, then this implies that the Mach number scales as Knudsen does. Yeah? The Mach number scales as Knudsen, and the Mach number is proportional to U. And basically, this should give the explanation why CS square is proportional to 1 over Mach number. For this fixed, I think this was the reason, yeah. Okay, something else that annoys a lot of people, mathematicians in particular, the Navier-Stokes equation. So if you are a mathematician, or the way mathematicians usually work, applied mathematicians by that, yeah. So they get an equation. They don't have any relationship to physics. They didn't learn physics. Yeah, they get an equation, and their purpose is to solve this equation. Yeah, so maybe they don't care. I mean, some of them don't care whether this is the truth, and some of them think they do this because this is the truth. But it's very important to know that the Navier-Stokes equation is not the truth. The Navier-Stokes equation is a model, and is a very good model of nature. But you already noticed it cannot be true because it assumes that Knudsen number is larger than 0, but otherwise the Knudsen square is 0. And this leads to some problems with all of this, namely that we have some observations that contradict the Navier-Stokes equation. So in physics, basically, if you have a single experiment that is in contradiction to your theory, the theory is dead. Okay? But the solution to this is you say this is not a theory anymore, this is now a model. Because a model can be incorrect. For a model, it's just the question whether it is good enough to solve a specific problem. Yeah? But if it's supposed to be a theory, you do one experiment that is not predicted by your theory, the theory is dead. Yeah? So, and for the Navier-Stokes equation, the Navier-Stokes equation used to be a theory, if you will. Yeah? So for people like Mach, but we found things that don't actually work. So important, and they're pretty simple things that don't work with the Navier-Stokes equation. So according to the Navier-Stokes equation, it is impossible that two bodies can touch when they are in a fluid. And the two bodies Boltzmann, wo? Das weiß ich doch nicht. Des Empfängers. Du bist bestimmt nicht der Empfänger, oder? Doch, vielleicht. Signatur des Empfängers. Okay, wenn nicht, dann nochmal. Ja. Politics. Okay, according to the Navier-Stokes equation, it is impossible for two bodies to touch. So, and I've done a lot of discussions. Okay, let's first look at two bodies. Yeah, say we have body number 1. So this body moves. I mean, if they don't move, they would not touch. Yeah, but say there's one body and there's another body with velocity 2, and they go in opposite directions. So they go in opposite directions, so they will finally touch. Problem is there is a fluid, whether this is air or water or whatever, is in between. Yeah. And of course, you know lubrication. You put some oil into your gears so that they don't touch. Yeah, and apparently this sometimes works, that they actually don't touch. Yeah, so they stay lubricated. But sometimes this fails, apparently. And according to the Navier-Stokes equation, it is physically impossible to fail, that things touch. Why is this the case? The case is that we have a small, say, layer of fluid around the body, and in this layer, the velocity close to the body's surface is the velocity of the body itself. So there is no slip. So according to the Navier-Stokes equation, without now trying to solve them, when these bodies get closer and closer to each other, get closer. So there is a closing gap between them and a non-zero velocity. This implies that the pressure between them, or in the gap between them, this would increase, and the important thing, it would increase indefinitely, yeah, and then drive them apart. So we would have a singularity in pressure. The pressure would get infinitely large. And actually, I find it always amazing that I find so many people that insist that this is actually true. Because, I mean, it's not so obvious that this may not be true. Yeah. So, do we know that bodies can actually touch? Yeah. I mean, it could be that I'm not standing on the floor, but there is some high pressure air between me and the floor, right? So how we know that this is not the case? So this is something you can think. How do we know that bodies can actually touch? Can you give me an experiment that, or say that things, if you don't like the word body, that things can actually touch? Simple experiment.
Clapping your hands.
Clapping your hands, no. Clapping your hands could also, I mean, I now have my hands together and there could still, I mean, I think I have them together, but there could be air in between them, yeah? Okay, I give you, yeah.
Well, I just have a question. The thing here is that we're comparing the assumptions made in the kinetic theory and...
No, we are not talking about kinetic theory at the moment. We are saying, okay, we are talking, I give a little bit of motivation why there is something more than Navier-Stokes equation. Yeah, so the Navier-Stokes equation, for most parts, if you want to calculate the track of a car and so on, you are not concerned with movement of bodies and what happens if two of them, get into contact.
Okay.
Yeah, so this is usually, so often you don't have this problem, but consider you have this problem. Yeah, so it is now difficult to say. So, for example, I'm clapping my hands, and whether there is air in between or so, I don't know. I mean, I know one condition where I can say that two things actually get into contact, and this is if I take, say, an ocean and I take a raindrop. Yeah? So when the raindrop actually merges with the ocean, so that it goes into the ocean, then obviously it has had contact. Yeah? And actually what you can observe sometimes is that a raindrop bounces off the surface of water. Yeah? So it's actually possible that there is enough air in between and the pressure gets large enough that the droplet does not actually touch the water, but it's bouncing off. However, you know that after it has bounced off 4 times, it will then usually merge, and the Navier-Stokes equation says this is impossible because there's always pressure in between them. Yeah? Always pressure that's driving them apart. So the Navier-Stokes does not permit the merging of the drop and the ocean. So, and now important to understand what is the problem here. So again, this is the ocean surface, and there's a droplet. And then between the ocean, so the droplet is going down, and between the ocean and the droplet, there is a gap. And for the purpose of the problem, whether the pressure is driving apart the ocean and the droplets, the important length scale is the distance of this gap, obviously. Yeah. So this is the physical meaningful length scale, and this has to be brought into perspective with respect to the mean free path. The mean free path lambda, which is used to define the Knudsen number, and how you see what the problem is. Yeah. So the Knudsen number, lambda by L, yeah, we have seen that the Knudsen number must be very small in order for the Navier-Stokes equation to be true. But this is not the case in the gap. So in the gap, the Navier-Stokes equation is not valid unless L is much larger than lambda. And if you are able to use open form in order to simulate a two-phase model with open form in order to merge two droplets, this is only possible because the two-phase model in open form is not faithfully solving the Navier-Stokes equation. Yeah? So basically, they know that the because you know that the Navier-Stokes equation is not correct, you simply ignore the Navier-Stokes equation when two things get close enough together and say now they merge. But if they would faithfully solve the equation that they are supposed to solve, the droplet has to bounce off, yeah, because it's not possible for them to merge in the Navier-Stokes world. But the Navier-Stokes world is basically not correct in a gap, because when bodies get closer to each other, or objects, okay, let's say objects, objects get closer and closer, we will finally get to the condition that lambda is larger than L, and then obviously the Navier-Stokes equation is no longer allowed. And for air, this is roughly at normal pressure. Yeah, so this depends on the pressure, of course, but at normal pressure, this is something like 60 nanometers. Yeah, so when things get closer, so if a gap is closer or in the range of this 60 nanometers, then you cannot use the Navier-Stokes equation anymore. But you see that 60 nanometers is pretty small. For things that are further apart than 60 nanometers, Navier-Stokes limit is very useful in many applications, obviously. Yeah, but just know the limits. And I mean, merging droplet is not completely exotic. Yeah, it's not like entrance of a space vehicle. Yeah, it's things that you can do in your kitchen that prove that the Navier-Stokes equation has its limits. Okay, I have taken up half an hour bashing the Navier-Stokes equation. Sorry for this. Yeah, but you have to have a reason why you go to kinetic theory. Now let's write down the Navier-Stokes equation in terms of these Boltzmann moments. And here again, this is from last lecture. So in the last lecture, we said that the Navier-Stokes equation written in moments was dt m100, this is basically the momentum, is equal to dx m200, so the second moment, equilibrium, minus dy m110 equilibrium minus dz m101 equilibrium. So these are the second moments. And then there comes tau. We had 1/3 here, dxx, so the second derivative in x, of the third moment in equilibrium, plus dy m120 equilibrium plus dz m102 equilibrium. And in this simplified version now, I already made use of the divergence theorem and considered this incompressible. Yeah, so that last time we had this question: what is this this bulk viscosity part in the Navier-Stokes equation that was not recognized by all here, and this is something related to resistance against compression, and we now assume incompressibility, so this term here drops out. Yeah, because if we want to consider the incompressible Navier-Stokes equation as the thing that we want to solve. So, when this is the case, what we observe is that the highest moments in our moment hierarchy appearing are the third order moments. And they only in equilibrium. So M3 0, 0, 0, M20 and M120 and M102, and potentially more of them, they are all third order. So then what this means as a general idea is that if we have an approximation of the, or more or less any approximation, of the Boltzmann transport equation that retains up to third order moments, or the equilibrium, because they are all equilibrium moments up to a third order, then we should be able to solve the Navier-Stokes equation with this thing. So after now bashing the Navier-Stokes equation for so long, I have to tell you that what we are now doing with this up to third order moments is nothing else than solving the Navier-Stokes equation. Unfortunately, if you do Lattice Boltzmann and you think you're solving the Boltzmann equation, you are, I mean, in that you have an approximation until a low order moment, and this is the same level of approximation that you get in the Navier-Stokes equation. So with Lattice Boltzmann, we are not actually solving the Boltzmann equation, we are solving the Navier-Stokes equation with this method. There is no, so these things that the problems that the Navier-Stokes equation has will also appear in the solution of the Lattice Boltzmann method, because the Lattice Boltzmann method solves the Navier-Stokes equation, because we go only to moments of third order. Okay, let's see how this looks like in one dimension. Discrete velocity model 1D. Okay, now we actually come to the interesting topic. So if you're actually only interested in the methods and you don't care about kinetic theory, yeah, so now you can actually open up. For describing these discrete velocity models, especially in one dimension, we use something that we call the characteristic diagram. And this is potentially something that, again, you don't find in the book. This is a little bit Martin Geyer style. It's supposed to give us some understanding what we are doing. So characteristic diagram. This can only be easily drawn on paper in one dimension of x, and here we draw dimension of t. And I'm an old-fashioned guy and draw this t downwards, because this is how originally the cellular automata were drawn, from the top downwards. Yeah. Okay, so this is just a convention, and you may have other ideas on conventions. So in 1D, so we assume that there is a Cartesian grid in space. This means equally spaced lattice nodes. Yeah, so they exist at multiple time levels. So there's discrete space, and there's a discrete time. So, and the spacing in space is delta x, and the spacing in time is delta t. And between these nodes, there are populations moving around, and these populations, so for example, there's a population that goes straight, so this is not moving in space, so it stays on the same lattice node for the next time step, and then there is one that is going to the left in one time step, and then there is one going to the right. And this is then true for all of them. So now we can spend the rest of the day drawing these lines here. So there's particles going in all these directions. So this diagram is sometimes useful to get to understand some special cases, in particular what happens in the boundaries. Yeah, so how do we connect to boundaries? So this is one thing we are going to use it for. And also to identify where things are happening. So we'll soon introduce the two steps that we are doing, which we call streaming and collision. And you see that we have here particles streaming, so between time steps, and then we have them colliding, and then we have them streaming again. Yeah. So this is streaming, colliding, and then here is a collision again, and here is a collision again. So characteristic is, there is here delta x and delta t, and together this is c, so c is the velocity, yeah, delta x by delta t. This we call the lattice velocity, and later we will put this for the purpose of simplicity to 1 in order not to keep track of this all the time, which is a little bit unfortunate because this leads to the equation looking like dimensionally inconsistent, yeah, which of course goes bad into my heart, but this is the way it's usually written down. Okay, yeah, this maybe often seen in dimensionless. Actually, it is important for the computation that these things are in dimensionless form, yeah, because you as a student, and I've seen this a lot of time, yeah, may try to use physical units for velocity. Yeah, it's very important that you don't do this in Lattice Boltzmann. Yeah, so the velocity in the Lattice Boltzmann equation has always to be given in delta x by delta t. So this is the natural unit of this method. Otherwise, it does not work. Okay, so in this model, what we have is look at the green one, yeah, where the particle could stay where it is, or it could go to left and right. This means we have 3 discrete velocities. So we usually call the velocity, because we are in one dimension, is no vector now anymore. So this velocity xi is then I times c, which is of course I times delta x by delta t, which when we put this to 1, then it's of course just I. And I in this case is in the range -1, 0, and 1. So these discrete numbers. So, and as I just said, there is these 2 steps in this algorithm. One is called streaming. So what happens is that particles move with the velocity I times c, so delta x by delta t, with I being an integer, and this means that the populations populations is the number of particles saying that are moving in this particular direction, yeah? Or the probability that a particle is moving in this direction. Yeah? So these are 2 equivalent ways of thinking. Yet the populations, they hop from node to node on a regular grid, because they just hop We don't need to do any interpolation or anything else complicated, yeah? It's just, there is data, we take this data from here, we put the data there. What is inside the data, we don't care. So this is streaming, and then the intelligent, so this is the stupid part, and the intelligent part is the collision. The collision, particles interact with each other on the nodes. So the important thing here is on the nodes, which means that only particles that are locally at the same location interact with each other. They don't look at their neighbors. So what happens here is that this is a rearrangement of the populations under conservation laws, of course, that we can specify. So this is implemented using the moments, so conserved moments on this lattice node. They stay the same. Non-conserved are changed by whatever rule we come up with. So, okay, so talking about moments. We have already talked a lot about moments, but we have always talked about moments in a continuous space and in multi-dimensions. Now we're talking about moments in one dimension, so MA. So this is not the Mach number. This is M index A. This is the integral, now only one, from -infinity to infinity. So, and how do we now represent these discrete velocities? The discrete velocities are written as a sum over the populations Fi times the Dirac delta function of IC minus the velocity xi. We multiply this over xi by the power of A and integrate over xi. So now I hope that you guys know what the Dirac delta is. The Dirac delta function is indeed, no, it's not a function, it's a distribution. The Dirac delta distribution is in fact defined by its integral. So if we integrate over Dirac delta function times a function xi, and the xi, what comes out is the function out of this integral is the function at the location where the Dirac delta function is 0. Yeah, I guess this is something that somewhere you've already learned. So, which means if we apply this here, we get this integral to just being the sum over Fi in IC and this IC by the power of A. This is now the simplified version. So we're coming from an integral to a sum in the discrete world, which is not too much of a surprise, I guess. Okay, describing, so let me write it down. So then there would be a zero moment. So the zero moment would be the sum over I fi by the power by ci by the power of 0. So this would obviously get. By the way, when you implement these things, right? When you implement these things, then we do the assumption that 0 by the power of 0 is 1, right? Because this, if I is 0, then you would have 0 to the power of 0. And for our purpose, now you can argue with a mathematician, but for our purpose, this would be considered to be 1, okay? So that we can actually write f minus 1 plus f0 plus f1. And this minus 1 written like this, so we write it like this, this comes from, there's the negative, it's the negative lattice direction. Which actually is going to make more sense once we come into the world of three-dimensional lattices. These are Miller indices. So I actually don't want to now get too much time, spend too much time onto this, but again, for those of you who like to look into the books on Lattice Boltzmann, this way of writing directions is not the original way that you find in the original work. So they want to have one index and they count from 0 to whatever, 3, for example, yeah. And they always need, all these people, when they start, they have a sheet of paper or something on their wall where they can look up which direction has which number. Yeah, and then they are very, very clever. Then after 10 years, they have all of this in their head. Yeah, so the thing is, two people defining this would always get to a different ordering of these things. Lattice Boltzmann. So lattice is the idea is that we actually model our discretization on a lattice, on a crystal, right? And crystallography has solved the problem of how to describe directions for 200 years. And this is unique, and you can learn it in 5 minutes. Yeah, and this is called Miller indices. So Miller indices are the integer vectors in. So you don't normalize them, but you put for each direction that you have, you multiply them by a number that makes all of them integer. Yeah, and the ones that go in negative direction has this bar on top, which is the minus. Yeah, so this is something very, very easy that has been used for 200 years to describe lattices, and because we are in Lattice Boltzmann, we should just use them because they are simple. Okay, so this is our moment number 1, the zero moment. So it's the first. It's the first that we compute, and this is number 0. Moment number 1 is then minus. So there, if we have 0 by the power of 1, that this vanishes, right? So we have only minus f minus 1 plus f1, and this multiplied with c, and we'll later put this c being equal to 1 again in order to get rid of this, because otherwise it's going to be annoying. And the second moment, so how do we get to the second moment? Ci by the power of 2, yeah, so we have it once with minus and once without minus, but we take it square, so it will be just f minus plus f1 and this into c square, and then things continue with m3. So because I is either is -1, 0 or +1, yeah? So if we take this to the third power, we again have the same thing that we had at the first power. So it's going to be this here, it's just c by the power of 3, which is a constant, which we later put to being 1, so you can actually forget this. And then m4 is an even order, so we get again the same thing as with the second moment. Is this clear to everybody? Now, what you see here, so I made this 1, 2, 3, and then I stopped. The thing is, we have 3 populations, so you already know that you can have only 3 independent moments. Yeah, so you can turn there's a conservation of information. So what you observe is that this guy is reoccurring here, and this guy is reoccurring here. Yeah, so they are reoccurring, and this reoccurrence, this is called moment aliasing. So aliasing always means that there is an alias. So there is one thing that has 2 different names. So exactly the same information, M1 or M3 is just another name for M1 in this case, and M4 is just another name for M2. And the reason here, let me write this down, there's 3 discrete velocities, meaning, wait, there was 3 independent moments. Actually, I had the intention not to take overtime today, but I will have to take overtime today. I'm too slow, sorry. So, we have a little bit of problem. For the Navier-Stokes equation, we need up to third order moments. So we need M0, M1, M2, and unfortunately we need M3, which O is not which is just another name for M1. Okay, so that's a bit of a problem. M0 is the mass, so this is a conserved moment. M1 is the momentum, which is also conserved. And M2 is the energy, so is the energy conserved. actually we have a problem if energy is conserved, because then all the moments are conserved, and then we have no possibility of changing anything. Yeah? But there is another thing. Energy, you would now say, when I ask you, is energy conserved? Then you say, of course, energy is conserved. However, not in the Navier-Stokes equation. The Navier-Stokes equation does not care about conservation of energy. You can supplement the Navier-Stokes equation with an energy equation that is usually called the Navier-Stokes Fourier equation, yeah, and that is supposed to conserve energy. But the Navier-Stokes equation in itself does not conserve energy. And the reason is that there is viscosity in it, and now we have assumed here in our derivation that the temperature is constant. So you can conserve energy if you take into account that viscous friction generates heat. Yeah. So you have to trace your heat in addition to it. Yeah. Yeah. But the Navier-Stokes equation, heat just drops out. Is another thing why the Navier-Stokes equation is not correct, because it does not conserve energy. Very simple. Okay, let's try to use a discrete BGK equation. So where we have M0 equilibrium is, because it's conserved, always conserved moment the same is rho. M1 equilibrium is conserved, so it's the same as rho times u. And M2 equilibrium is according to what we had, rho times c s square plus u square. So this is something that we derived, I think, 2 lectures ago. And now the equilibrium for the third order moment. This is also something that we have already derived, was 3 times u times rho times cs square plus u square. Okay? So you can go back in the lecture and we had this. Okay. Problem being that M3 is not equal to M1, right? So how can we repair this? There's 2 things that need to be done. First of all, so there is a third order part in velocity. Yeah. What we can do in order to get rid of this is assuming, of course this is not correct, but we assume it. Oh, okay, is it correct? So we say we are only interested in small velocities, okay? We are only interested in small velocities, and if we are only interested in small velocities, what am I doing? We can assume that u by the power of 3 is 0. We know then that we introduce an error with this, okay? But if this is small enough, yeah, we can do this assumption. So then what we have next is 3 times u rho cs squared. Okay, and now how can we repair this? We have de-Aliasing. We have this thing. It has to be 1.
Yeah, the CS are, I mean, it's going to be 1, right? Because we have the
So yeah, that needs to be 1. So how do you get it to be 1? What is cs square?
It's the...
No, it's the speed of sound. I know that this is k Boltzmann t by m, yeah? But so what is it now for, now what value does it need to have here?
It has to be equal to 1/3.
It has to be equal to, actually it has to be equal to c square over 3, right?
Okay.
Yeah?
Yes.
So, if we, but you're right, I've already said a couple of times that we assume, yeah, we say, so, say this is a dirty, yeah, evil, have a bad, okay, it's not a very beautiful devil, yeah? Okay, but anyway, you could say this is c is equal to 1, and then we, yeah, basically we define the speed of sound is 1/3c, square root 1/3c. So this is because we have too little degrees of freedom to do it otherwise. Yeah. So you see, this is related to the temperature. Cs square. We fix the temperature. We fix the temperature to a specific value that allows us to get along with 1 moment less. So then, okay, running short in time, we want to translate between populations and moments. And here I'm a bad guy and I'm using c equal to 1. So m0 is then, as we've already said, is this, m1 is this, and m2 is this here. So now we can simply rearrange this as f is equal to m1 plus m2 half. Of course, so this is because we took out the c. Otherwise, you would see this is not a unit dimensionally consistent. But in the computer, I mean, we want to implement this on a computer, and in a computer we deal with dimensionless numbers. So it's always difficult for me in physics to teach you to use dimensional numbers, and then in computer modeling you always use non-dimensional numbers. So our equilibrium is m0 equilibrium is rho, m1 equilibrium is rho u, and m2 equilibrium is rho 1/3 plus u square. Yeah, and here again you see this would actually be c square, but we assume that u is already, I mean, this implies that u is given in units of delta x by delta t. So this is very important. You cannot write u in terms of meters per second here. So if you enter this into so if you rearrange this, so you take these equations here, you put in the moments you get for the equilibrium distributions, rho half u plus 1/3 plus u square, you get for the minus version of this, you get rho. Here you get minus u, that's the only difference, plus u square. And for the F0 equilibrium, you get rho 2/3 minus u square. And now let us see whether we can manage the Lattice-Boltzmann equation in the last 20 minutes or so. Lattice BGK. So this is a special form of the Lattice-Boltzmann equation. It only uses the BGK operator, because this is simpler. Lattice BGK equation. So let's look at again the streaming. So what happens in streaming? We have Fi, we have a location x plus IC delta t. So in one time step we move the distance IC, yeah, depending on in which direction we are, and we go one time step on. And this is equivalent to what came out of the last collision at the location here and now. Yeah? So this is the streaming equation. And then there's a collision equation. The collision equation is F after collision I at the position x and the time t is Fi, so the incoming, the pre-collision state at the same location plus an relaxation parameter. Now this we call omega, so this is basically something like the inverse of the mean free time, but we'll come to the detail later. X t minus Fi equilibrium, and here again the incoming part. So you recognize this as basically the BGK equation with just instead of 1 over tau, we have written omega here. So it's the frequency instead of the time. Yeah. So this is the post-collision distribution. And this is the pre-collision distribution without this asterisk. And omega is the collision frequency, which is the inverse of the mean time between collisions, but don't write it down yet because we'll have a change to this later. So these are the equations S and C. And now for convenience, we do a shift of variables in the streaming. And this looks like this. Okay, so the problem that we have is we have our equation here is a little bit asymmetric, yeah. We have it here and now on the right-hand side, and then we have the movement in space and time on the other side. Now there's different ways you can rearrange this, and one way this was originally rearranged was to have it moved in, to have the movement in space on the other side, which you can basically do by just putting it here and writing it with a minus, yeah, so that you have it there and now, and going to here and then, yeah, if you will. But the thing that is from a mathematical point the most useful is to make it completely symmetric, and we get it symmetric if we move it to these half steps, which is also consistent with our characteristic diagram where we have the where we have the particles collision during the streaming, the particles position during the streaming in between the nodes, yeah, and in between the time, yeah. So this is why we do now this half shift like this. We have plus IC delta t half, and we go half a time step. And okay, and what we do in addition, we put everything on one side. So I take this minus Fi after collision, and here I do it in the opposite direction, delta and t minus delta t2. So, I mean, I hope everybody can agree that this is saying exactly the same as this equation as above. Yeah, it's just written in a different way. And the collision can also be written in a slightly different way by saying that this is the after collision part here, minus fx and t, and this is equal to omega fi equilibrium x t minus f minus fi x and t. Okay, so what we do now in order to get the equivalent partial differential equation that we are solving with this is we are using a Taylor expansion of the S equation. Yeah? And this Taylor expansion of the S equation is of course a Taylor expansion in both x and t, obviously. Yeah? So Taylor expansion of the equation S at x and t. So this means, so I put the 0 that is now on the right hand side, I put this to the left, yeah, so that we start off with this, and then we expanding this at the location x and t, and if we do this, we have of course first the local part, yeah, so this is the, yeah, this is clear to everybody, hopefully, yeah, plus, so now we have to expand both in space and time, and now we start with expanding in space, and the distance that we are in time, we start with time, sorry, yeah. So we are moving a distance delta t half. So I write the delta t half before, and then I have the time derivative, and then I do this for both of them. Yeah. So I go into positive direction for the pre-collision part. Yeah, that comes first. That is fi xit, and then I have to go into the negative direction for the post-collision. Parts. And because there is a minus in front of the post-collision parts, this will cancel out, and I will end up with this plus here, okay? So, and now you will easily see that something very similar, yeah, is the case also for the space derivative, yeah? So I write the space derivative is in I delta tc, divided by 2, and this is now just in dx, and the same thing applies here for the directions. Yeah, because once I go in positive way and then I go in negative way for the negative part, so they both end up as being positive. Okay, so this was the space thing. Then we go a second term, which is I delta t. No, in time. We begin with time. we begin the second delta t by the divided by 4. Now it's the 1/2 comes from here, and the other is 4 actually correct? Let me see.
I think it's 8.
It must be 8, right? Yeah. Okay. So sorry for my. Should be 8. Yes. So okay. In this case, we are going delta t square for the pre-collision part. It is all positive. In the post-collision part, up here we have a minus in front, but we now take the square of minus delta t. Yeah. So the minus will remain. Yeah. And now we've discovered that I made a mistake here, so we'll have to write I delta tc square and obviously divided by 8 dxx. So the same thing applies also in space, so therefore there will also be a minus here. Okay, and this of course goes on forever, but we'll continue with just one more with the mixed term. Yeah, so the mixed term looks like this. So in the mixed term it will be 1/4, right? It will be 1/4. Then dxt. So to the mixed term, there's the same thing applies because so mixed derivative dx dt, yeah. So we go twice in positive direction for the pre-collision part, and we go twice in negative direction for the post-collision part, and therefore this minus will remain here. Okay, I hope that this was not too fast for everybody. We have remainder terms of obviously order delta by the power of 3. Okay. Now there is one thing that we should recognize is that this here in front is minus what we had as the equation C. Yeah? It's just the opposite sign. So there's basically the collision operator here. And the other thing that we now do as a new introduction is we define f over bar as being fi plus fi asterisk. So this is the average between pre and post collision. Yeah, because in the Boltzmann equation we don't have pre-collision and post-collision. We only have the distribution. So, by the way, there's a warning here. My colleagues are very mad at that I define things like this, because in other literature, the pre-collision distribution is defined as over bar, and the one that has no over bar is what I call over bar. And then there is, lots of fighting who is right. I take the liberty, because this is my lecture, to use my way of writing it down. I completely acknowledge that just twisting the same notation around in literature, that there's two ways, one driving left, one driving right, is a problem. But this problem already, is spread all over the place. So, Gaia notation. Remember, if you look into another paper, look up what their notation is. Yeah. Okay. So if we define these things, so this thing we don't have in the equation. So what we have in the equation is, of course, the pre-collision state, and we can rewrite this now, of course, like this. This is the average overbar version minus 2 times the overbar version minus, yes, it's just rewriting this. And this can again be rewritten as fi half plus fi overbar minus fi star half. Yeah? So this is just rearrangement of the same thing, and this rearrangement of the same thing is now used in what we have in the C equation. So the C equation again is, here we have post-collision minus pre-collision is equal to omega FIEQ minus F pre-collision. And now we replace this F pre-collision with what we have just written here and get to Fi minus Fi asterisk half minus Fi overbar. Okay? So, looks a little bit strange why I introduced this, but the reason is that I have this guy here and here, yeah, and I can recombine them. I can recombine them by writing this is Fi asterisk minus Fi, and when I recombine it, I have 1 minus omega half is equal to omega Fi equilibrium minus Fi overbar. And this can be written as Fi post-collision minus pre-collision is equal to 2 omega divided by omega minus 2 Feq minus Fi overbar. So, and now you could say, so this is the change, I mean, the difference between after collision and pre-collision. Yeah, this is the collision operator. Back here, we have everything now written in, not in terms of pre or post-collision distribution, but in the average, yeah? So to speak, at collision time, the population at collision time. And now we have a new prefactor. Yeah, remember in the original BGK equation, there's 1 over tau here. And now we have 2 omega divided by omega minus 2. Okay, when do you have to leave?
When does the lecture end?
It should be ending in 2 minutes, but I'll need a few minutes more because it's, so if you leave, you just watch the recording. So our equation 4.1, I don't remember whether I put actually 4.1, sorry for messing things up. Where did I put the equation 4.1? Okay, I wanted to say that this is equation 4.2. Equation 4.1. Yes, I think I forgot this. I said this is 4, we put this 4.1. Yeah, the big one is 4.1. So, going back to equation 4.1 is Fi after collision minus Fi. So now delta t dt. So what we see, we had in here, we have 1/2 the sum over pre and post collision, right? In the time derivative. So this simply becomes now dt f over bar, plus the same thing applies to dx fi over bar, and the only place where we have the difference still sitting is in the second derivatives, which I miswrote before. So this is dtt fi minus fi asterisk plus the other second derivatives, dt ic squared divided by 8 dxx fi minus fi asterisk, and now the mixed term dt square, thank you, divided 4 minus ic, now the mixed term, mixed derivative dx and t, into minus fi minus fi asterisk, so after collision, and all of this comes with a rest term of order 3. So now there is an important observation to do. Everything on the right-hand side of this equation is at least of order delta t, right? So this means that we can also write that fi asterisk minus fi is of order delta t. And then we have other parts here, so the second derivatives, say delta t square, which was divided by 8, if we want to write this, dt t fi minus fi asterisk. So we observe that in here we have something that is of order delta t. And we already said, also we have here, rest term is of order delta t cube. And we have delta t square here, and we have something delta t here. So this is of the same order as our rest term. So it's actually necessary to eliminate them. Yeah. So you cannot leave one term of that order inside and put the rest to the outside. This is not proper mathematics. Which means we can rewrite this thing, and now I call this 4.2 as being fi asterisk minus fi. So this we have already identified recently to be 2 omega divided by omega minus 2 into fi equilibrium minus fi over bar. And now the rest of equation 4.1, that's still here, dt delta t dt fi over bar plus delta t ic dx fi over bar plus the rest term that is of order 3. Okay, so in this can then be rearranged by dividing by delta t, dt, see, not messing it up again, dt fi over bar plus ic dx fi over bar is equal to 1 over delta t 1 over omega minus 1/2 into fi equilibrium minus fi over bar, and this O now of course of second order, because in order to get this we had to divide. In order to get this we had to divide by delta t. Okay, and I've rewritten this here in the prefactor in a different form, so that I can declare this to be the BGK equation, the BGK equation for actually f over bar. So and I just said that this is my nomenclature, but the fi over bar, I use the over bar because this is something that that does not exist in the methods. Yeah, in the methods we only have pre-collision and post-collision, and not this fi over bar. But the equation that pops out, the BGK equation that pops out, is an equation of this fi over bar. And here we identify that we have this tau must be 1 over omega minus 1/2 delta t. So obviously tau is not, as we would otherwise expect, the inverse of omega, so delta t by omega. So this is not the case, but it has this correction, which was first discovered by a Frenchman called, I cannot pronounce it anyway, Eon, and therefore it's called the Eon correction. The Eon correction. Okay, so this is a very important equation, yeah, so that we need to know for computing the viscosity. Okay, just the few last words. The stencil, there's a nomenclature on the stencil that looks like this. So now we have three velocities, f0, f1, and f minus 1. And this thing is called a D1Q3 stencil, where this nomenclature DD, QQ is the D is the number of dimensions, and the Q is the number of speeds. So there is 1 dimension, 3 speeds, and then there is something that's called, for higher dimensions, there are different lattices, but one of them, or one kind of them, are the tensor product lattices. Tensor product lattices, they go like this. They have DD, Q in 1 dimension by the power of D, which would result in 2D. So 3 by the power of 2 is equal to 9. So in 2D, we would have a D2Q9 lattice, and in 3D, we had 3 by the power of 3, which is 27. So here we'll have a D3Q27 lattice. Yeah? And how these things look like, we see then in later lectures. Okay? Thank you for listening. I'm going to stop the recording.